Hello, today we want to talk about resonant frequencies. By now, we've talked about elements in series in a circuit when you have capacitors, inductors, and resistors. We know what the impedance and the reactance of a circuit or the elements are, the total impedance. We know that the impedance is basically the reactance of the element and the phase shift produced by the element, and the reactance is the resistance of electrical current to flow through an element in AC circuits. So knowing that, we want to, first of all, be able to understand the contributing factors for resonant frequencies, and we want to understand the frequency response of passive elements, such as inductors, resistors, capacitors in series. So we know by now that when you connect passive elements in series and you apply a source with AC current and AC voltage, you have a response in the frequency domain because of the reactance and the total impedance of the circuit. So if you were to vary the frequency of that source, because remember before we had a single frequency, but now we want to study what happens when you start varying the frequency of that source, kind of like a variable frequency drive would change the frequency of the controller to change the velocity in the motor or the speed within the motor. So we want to get my stylus. Remember that if you were able to draw the response, the reactance of the passive elements, the common ones such as resistor, inductor, and capacitors, you would have on the x or horizontal axis, you would write the real components, and the vertical or y-axis, you're going to have the imaginary components. So for a resistor, you have no imaginary um, component, you have or no imaginary contribution. All the contribution is going to be in the real axis. So it's going to be just resistance. And if you were to plot that in terms of frequency, you would get that it's a uniform behavior. You vary the frequency, you get the same resistance. Um, that in practice you would get, if you keep varying the frequency, at some point you might reach a point where the resistor is not operational anymore. So um, if you go to frequencies in the gamma rays or something like that, um, that's that's a different aspect. Right now, we're dealing with um, up until ultra high frequencies, so from hertz, kilohertz, all the way to megahertz, which is usually where you have your AC circuits. But in the case of the inductor, first of all, the response of the reactance because of the inductor, it's going to be a linear response because you have everything is a linear combination of the coefficients times 2 pi. So 2 pi is a constant times the frequency, which you're varying the frequency, times the inductance. This is the part that you buy. This is the inductance of the element. Okay, if you were to draw that on a real and or a phasor diagram with real and imaginary axes, you'll have all the contribution of the inductor because of the reactance being placed on the positive imaginary axis. Okay. For capacitors, you have an inverse relationship between reactance and frequency because it's 1 over 2 pi times frequency times capacitance, everything denominator. So notice that at higher frequency, lower reactance. And if you draw that on a phasor diagram, you can have no contribution on the real axis, but a negative contribution on the imaginary axis. Okay, that's why when you have a circuit and you start adding them together, you end up with a phasor diagram where you always have your resistive element, and then you have a summation of the inductor and the capacitance. If the inductor value is higher, you're going to end up with a positive imaginary contribution. If the capacitance value is higher, you're going to end up with a larger negative contribution. So when we start looking at circuits with just RC, or resistor and capacitors, we're gonna just look at the same thing. So for example, we have a source that is 10 volts in amplitude or magnitude, but then we're gonna vary the source from 0 to 20 kilohertz, and there's no offset, 0 degrees phase shift. There's going to be a fixed 5 kilo ohm resistor, or 5,000 ohms, and there's going to be a fixed 0.01 microfarad capacitor. Okay, we want to know what is the frequency response, what is the total reactant, what is the total capacitance, this is Z, total capacitance, and the voltage drop through the capacitor. Okay, so let's go ahead and use Excel for this. Okay, the first thing we want to do is write down the values from the problem. They gave us 5,000 ohms resistor and 0.01 microfarads, 10 volt source. So the frequency, we're going to create a column where you have, I decided to do steps of 10. You can, if you know Excel, you can do just 10, 20, 30, and then you grab the, for instance, let's do another one here. Suppose I want to do my frequency 10 with fixed steps of 10. So by doing 3 steps is enough. And then you grab the bottom of the box, and then it will tell you up until where. Okay, so that's what I did. I took it all the way to 20,000 because that's what the problem says. Source varies from 0 to 20,000 hertz. I didn't want to start from 0 because if you remember, the reactance of the capacitor is 1 over 2 pi frequency. So if you divide by 0, you're going to have an issue. So just start from a small number. To compute the reactance is very simple. It's 1 divided 2 times pi, which is 3.1415, times the value of the frequency, which we're going to be varying, times the value of the capacitance. That gives me this column. So if you plot this column right here, you're gonna see inverse proportional relationship just as we saw. Okay. Then if you compute the total impedance, you simply have to do square root of the resistor squared plus the reactance of the capacitor squared. So we're going to basically compute the frequency like so, or if we want to compute the total capacitance, the total inductance, we just have to do the resistance squared plus the reactance of the capacitor squared. This is the total capacitance, and then all the total impedance, I'm sorry, not the total capacitance, the total impedance, and then that's what I did, and you just extend the column all the way through. So if you were to plot frequency versus in total impedance, you notice that it's going to start converging to 5 kilohertz, right? 5,000 ohms. It's going to start converging to 5,000 ohms, not hertz. Hertz is my x-axis, ohms is my vertical axis, my y-axis. So at little or small frequencies, the system behaves as a capacitive system. In the large frequency range, the system is going to behave as a resistance, or what is the word? Resistive with a V is going to behave as a resistive system. So this RC series circuit has a capacitive and a resistive response. The point where it shifts is called the resonant frequency. And the resonant frequency is basically computed by um, comparing the reactance of the capacitor by the reactance of the resistor. So if you type your your reactance from the capacitor being equal to the reactance of the resistor, and you find that frequency at which those values are the same, you find your resonant frequency. For this value, for this example, because of the values of 5 kilo ohms and 0.01 microfarads, the resonant frequency is about 3.18 kilohertz. And that's the point at which, if you look at the graph, where this is frequency, this is impedance, that is the value more or less where there's a shift in behavior between purely capacitive and purely resistive. Okay, so this is how you compute the total resistance based, or the total impedance based on frequency changes. Because of the frequency change, you compute the change in reactance, and based on the change in reactance, you're going to have that value within the square root, and you can compute your total impedance. Now, that's pretty much what we got here. We have the capacitive circuit at low frequencies before the resonant frequency, and then we have the resistive circuit after the resonant frequency. If you want, and this graph also shows that it's going to converge around the resistive value. For example, this is a good, Excel is a good tool to show you that if you were to change the value of the resistor to 3000, this graph is gonna shift down to 3000. It's gonna converge around 3000 ohms. But if you change it to, say, 10,000, it's gonna go up to 10,000, right? So that was a good example to show you that this is where the total impedance is gonna converge to. Similarly, if you wanted to compute the voltage, you simply have to apply the voltage. You have to only apply the voltage divider rule, where we have our circuit. This is a resistor, capacitor, ground, and we want to find the voltage across the capacitor. So we're going to do voltage divider rule, which is the impedance of the capacitor times the voltage, which is 10 amps, 10 volts, divided by the total impedance. We already have the total impedance, and we have the reactance of the capacitor. So basically, we have this capacitance reactance of the capacitor, we have the voltage, which is given 10 volts, and we have the total impedance. By doing this computation, you have this column right here, which is the reactance of the capacitor times the voltage divided the total impedance, and we want to do that throughout the frequency domain. And if you plot your frequency versus your voltage, you're gonna get this response. It's going to be 10, 1 times 10 times e to the 1 is 10. And then for small frequencies, you're gonna have pretty much a capacitive response of the voltage. You're gonna, at small frequencies, you're going to have voltage. You're gonna store charges because of the capacitor. But at large frequencies, you're gonna have a resistive response. And since we have a 5,000 ohm resistor and we have a 10 volt source, then the current is going to be um, around 2 um, amps. So basically, the point here is that you're going to have a larger voltage drop at a higher frequency. Okay, and that is pretty much what we noticed here, that at small frequencies, at 1 kilohertz, you have a capacitive circuit, and then at large frequencies, or relatively large, um, this is 20 kilohertz, you're gonna have a purely resistive voltage drop. All right, let's look at a different example. This is similar, except for instead of a capacitor, we're gonna have an inductor. So we know that the reactance of the inductor is going to be 2 pi times frequency times the inductance. And if you want to find the resonant frequency, we just have to make it equal to the resistor value. And in that particular case, we find the frequency at which those values are equal. And it tells us that for those values, we get a 7.96 kilo ohm resonant frequency. So I'm sorry, this is not kilo ohm, this is kilohertz. Okay, because this is resonant frequency, and frequency has units of hertz. So if you were to compute your reactance because of the inductor, you simply have to compute your 2 pi f times L. You vary your frequency, therefore you get a straight line. And when you compute your total reactance or your total impedance, you simply have to compute this square root of r squared plus your reactance squared. Okay, and then the graph is going to be increasing in reactance, okay, which is the opposite of the RC circuit, resistor capacitor. The RL circuit is going to increase the reactance because of the response of the contribution of the inductor. Notice that the inductor increases reactance when frequency increases. For example, we have a voltage source with 20 volts and is varying from 0 to 20 kilohertz. So they tell us that the resistor is going to be 2 kilohertz and the inductor is 40 millihenries. What is the voltage drop at the inductor? So the resonant frequency, you know how to compute. Basically R divided by 2 pi L, and that's telling us that is 7,957.7 hertz or 7.9 kilohertz. Okay, the total impedance is R squared plus the reactance of the inductor squared at the values given by the capacity by the inductor and the resistor. That tells us that it's 10.25 kilo ohms. The total um, impedance. So if you were to compute your voltage, you also have voltage divider rule, where it's going to be the impedance of the inductor times the voltage divided the total impedance of the system. Okay, so in this particular case, you simply have to write down the values of each of these quantities, and you're going to find that it's going to increase its voltage until it converges at 20 volts for high frequencies. Right? You have this value, you have this value, you have this value. You simply have to compute the voltage drop at changing frequencies. So for instance, at 1 kilohertz, the reactance of the inductor is 0.25 kilo ohms. So you would write down that value and it will give you 2.48 volts. The phase shift doesn't matter as much for this particular point. We just want to see the voltage change. So it's around 2.48, which is right here. At 5 kilohertz, which is right here, The reactance because of the inductor is 1.26 kilo ohms, and the voltage is 10.68, around right here, and so forth, and so on and so forth. You compute the voltage given the frequency change, and then you'll get this curve. Now, the RLC circuit, the resistor, inductor, capacitor circuit in series, is a combination of the capacitor response, the inductor response, and the resistive response. Okay, so the frequency, the resonant frequency, is now a contribution of the inductor and the capacitor. Is where the inductive curve and the capacitive curve intersect. The formula to find that is 1 over 2 pi squared of LC, and L being the inductance, C being the capacitance, and that's how you find your resonant frequency. So if you were to compute the total impedance and plot the total impedance as a function of frequency, you're going to find that you're going to have a capacitive response for low frequencies. Then you're going to have a resistive response at the resonant frequency. Then you're going to have an inductive response for large frequencies. Okay, so this is a very common curve. It's always present for RLC circuits.